cap, we have the parallel resistor to match the impedance, too noisy. We also use inductive load to match it, but also have good headroom. But the point is it might oscillate. Remember, we solved for the circuit, the equation, the numerator. And now we use this resistive feedback. Noise is still large, but at least we see that RF does not contribute too much to the noise. That is good, actually. Okay? But we want to go one more step. How about use common gates with inductive load? So here involves some review of EE124 materials. So we need to be review them, just learn them. That would be good. Common gate amplifier. What is a common gate amplifier? The input is at the source. The output is at the drain. Common source is input at the gate, output at the drain, right? So you see that input is here, output is here. So if your input is here, we want to look into the source. And our question is to ask, what is the input impedance? Now, I have this intuitive view. If you're interested, take a look. If not, we can solve the small signal model. Again, these are all on the YouTube video, right? E124 video. I put gate here, drain here, source here. Source is the input. Drain is connected to RD and then to ground. Again, Y is ground. I connect it to VDD. Small signal, AC ground, right? I keep asking the same thing, but I'm sure that in the exam, some of you kind of forgot. Here is also AC ground. We show you already because it's VB. Nice. Then we find the relationship between I in and V in to find the input impedance. Okay, you can do many things. How about KCL? I in will become negative GM VGS. They're in opposite direction. And what is VGS? VGS is just 0 minus V in. Polarity is very important. Do not say it is either V in. It's negative V in. Okay? Then you go through the math. R in equal V in divided I equal 1 over GM. Again, you need to memorize it. The best, right? Or put in cheat sheet. Well, turn out to be very similar to the diode connector MOSFET. The input impedance is also 1 over GM. Okay, but however, here we don't have channel length modulation. If you go through the derivation, it's much more complicated. It equals to R out of the transistor plus RD divided by 1 plus GM R0. And does it make sense to me? Yes, because if R out is infinity, then the top is equal to R out. And GMR is very large. I ignore 1. So 1 and R0 and R0 cancel. Then I got 1 over GM. That is exactly the same without channel length modulation. Okay? So I don't know if you can memorize it, but you take it for granted. R in is 1 over GM for common gate amplifier. Or whenever you look into the source, if the gate is grounded, this is about 1 over GM for a well-designed transistor. That is the intuition, okay? Now, if that is the case, then let's start looking at the matching. This is the circuit. We bias it here, so it is AC ground. Yeah? The input is to here. This is source impedance, this look in. And I just told you, what is R in when I look into the source? What is that? Thank you. I know you know that, right? But thank you for helping me. 1 over GM. Okay? And then let's take a look about this so-called inductive load. Now, first of all, you get 1 over GM, that is good, right? R in equals to 1 over GM. So to match the input impedance, which is easy, just set S equal to 1 over GM. Or in other words, GM equal to 1 over RS, which was what we did earlier for the resistive feedback common source amplifier, right? So this is easy. And it means it's easy to do that. All right, because this is 50 ohm. Again, I just need 0.02 Siemens for GM to match it. I'm done. I'm done with this part. Let's see a little bit more about this loading. First, I have C1, right? But let's talk about it. Resistor R1 you can consider, I don't know if I put it there, as the parasitic. Maybe I don't want to say this. This can be just something we actually we will see that later. You may actually purpose put a R1 there so that you get the gain you want later when you do this LNA, right? So let's don't call it parasitic. But what is C1? Where does the C1 come from? C1, we talked about this earlier. What are the two possible components? Do you remember? Where does it come from? Do I just put a C1 there, or is due to what reason? When I talk parasitic, then you probably can tell me, right? It is the output capacitance. This can be I just call it output capacitance, right? This can be CDS, CDG, the drain and gate overlap capacitance. Remember what I said in the last lecture? Or maybe also including the CDB, the body to drain capacitance. Okay? Anyway, and plus the loading. I'm loading the next stage. I have wire and also input capacitance, right? So this is the C1 that is there. I need to design it so that C and R and L resonant. What does it mean? It means I want them to resonance, so appear as infinite impedance. Okay, so what does it mean? Let's just look at the impedance. C equal to SL1 parallel 1 over SC1. The impedance of the inductor is SL1, impedance of the capacitor 1 over SC1, right? So this gives me, we did that last time already, so this is a good practice, right? Which is equals to SL1 divided by S square L1C1 plus 1. I think I did something wrong. What did I do wrong? And this is okay. Actually, I did it right, yeah. But in my cheat sheet, I was talking about the conductance, but let's keep this. How can I make this infinity? Let me just substitute J omega L1. What is the lower term when I substitute J omega L1 to S squared? Huh? Minus omega squared. J squared is negative. Yeah, do not forget the J squared. Okay, so it's 1 minus L1 C1 omega squared, right? So at resonance, I have omega, I call it this, equals to 1 over square root L1 C1, which you know that already, right? You learn from fundamental. It is 1 over square root L1 C1. We are going to operate at this frequency. But of course, we already have our choice. We say, I want to do 5.5 gigahertz like in the project. Then you find a way to match C1 and L1. Maybe you have no choice with C1. C1 is limited by the size of your transistor. And the transistor needs to be so large, so you have this GM equal to 1 over RS. So you have no choice. And your next stage, I ask you to have 10 picofarad load, maybe. So C1 is fixed. Then you design your L1 so that at 5.5 gigahertz, they got resonant, right? And when they got resonance, the loading is only R1. So that's why, and then what is the gain of this transistor? The gain of the whole circuit. I again decompose it into V0 divided by Vx times Vx divided by Vin. What is V0 divided by Vx? What is the output impedance divided by Vx? So maybe some of you forgot. It is what? GM. This is the gain of a common gate amplifier. So it's GM R1. Correct? Yeah, if you, I mentioned that before in another class. If you forgot, but you trust me, it's GM R1. And let me ask you again, then, how about L1 and C1? Why only pick R1 as the loading? Isn't that these are all impedance? Yes, resonance. Very good. Because it's at resonance. So this is very important, okay? At resonance. Right? You're going to design, you pick a L1. So it makes your calculation much easier. And what is Vx divided by Vin? 0.5. Why? Because we match it. So it's just a potential divider. GM1 R1 divided by 2. This is the gain. But I don't like GM1. I want to express it in Rs. So this is equal to what? R1 divided by 2Rs. Because I matched the network already. Okay? So good. So this is the gain. And the reason I want to find the gain, again, is just because I want to find the noise figure. Right? So let's start doing the noise figure. But before that, we need to review something again. So what we want to do is the gain of a common source with degeneration. So what does it mean? Now, this is still the gate. This is the drain. The source is here. But this time, the source is not connected to ground. We have a RS. We call it degeneration resistor. It actually has a negative feedback effect. It's also a feedback resistor, which we won't discuss. But the point is, if I have RS, what's the gain? Now, if I don't have RS, what's the gain of a common source amplifier? Negative GMRD. Similar to this one, right? GMRD. But it's negative. So I won't derive it. You can watch the video. But the main point is the gain becomes still negative GMRD, but becomes smaller, divided by 1 plus GMRS. Now remember, if RS is 0, this term is 0. So it becomes negative GMRD. Makes sense again, right? But so this is called common source with degeneration. So just memorize this. I mean, we will use it. V out divided by V in equal to negative GMRD plus GMRS, right? And I urge you to take a look. I mean, if you have not learned that before. So let's now look at the noise figure. Before that, I need to look at the noise one by one. Okay, R1. Based on what we have learned so far, what is the contribution? Or let's just call it output noise voltage, right? V out R1 square. It is here. Now, I'm not going to draw small signal model. I will just use inspection. And I challenge you to draw small signal model yourself. What is the voltage that I will see here if I have a voltage noise source? VDD is grounded, right? And then this is grounded. So this is open circuit. Just try to draw the small signal. Because this is grounded and there's no current, no AC current. You draw it, you define it's grounded. So this is just equals to 4 KTR1. That's it. Okay. Then I will also just look at the noise due to the transistor. Now, M1 has its own noise. But this time, we model it as the gate noise. Because if you put here, it makes things more complicated. You need to solve the circuit. So we find the equivalent noise at the gate. If you remember, do you remember we did this? If you forgot, let me quickly remind you. You have this device, right? This one is IN squared equals to 4KT gamma GM. This is equivalent to, I put a voltage noise at the gate with Vn squared equal to 4KT gamma over GM. Very difficult to see, but do you understand what I mean? Because they are related by transconductance. So this guy times GM squared should be equal to the drain current. Gate voltage times the GM equal to the drain current. But now we're talking about the square of the gate voltage. Then we times the GM square, it will give me the drain current square, right? And same for the noise. Voltage noise becomes it. So that's why we have this one. Why do we want to do this? Because we already know what the gain is. Because I know that the output voltage noise due to M1 must be equals to 4KT gamma GM, which is the gate noise power, times the gain of the common source amplifier with degeneration. Why have degeneration? Because I have the source voltage, a source resistor, right? When I try to find the noise, I need to short the input. So this comes from the source, the voltage source, or input voltage source. It changed my gain, and I just told you earlier what is the gain. I forgot one important thing. It's square, right? We're talking about power, A squared. So what's the gain? GM1 R1 divided by 1 plus GM1 RS. That's why I put it here. I have the gate's input. This is RS, right? So this is negative GM RD divided by 1 plus GM RS. That's why now I have GM1 R1 divided by 1 plus GM1 RS. I better put M1 here. It actually doesn't matter. I only have one transistor. So I need to do some simplification. This is very messy. Just remember what is the relationship between GM1 and RS. GM1 equals to 1 over RS. That is very important, right? So this gives me KT gamma divided by, or just times, or maybe divide for now, 1 over RS. And then GM1 times R1 means R1 divided by RS. And the bottom is 1 plus 1, right? Because 1 plus GM1 times RS. GM1 times RS is 1. So this one gives me what? 2 got cancelled, right? Let me use another color. This 2 got cancelled because 2 squared equal to 4. And then I have R1 squared divided by RS and then cancelled by RS. So I get 4KT gamma R1 squared divided by RS. I don't have 4, sorry. KT gamma R1 squared divided by RS. So what is the noise figure? Someone tell me, do you remember the equation now after working for so long, so many times? Is what? 1 refer to the input itself has a signal to noise ratio, all right? Plus 4KT R1 divided by the gain, right? The gain is a little, what do I get? The gain is a little bit complicated. Is R1 divided by 2Rs. We already simplified, right? Otherwise, pretty square. R1 divided by 2Rs square. Is that right? I make a mistake on it. Okay, times, that's why. 4kT Rs. Very good. Always normalize to Rs, right? And then the second term, the same. 4kT gamma. No, I need to copy the last term. Should be kT gamma R1 square divided by Rs, and then again divided by the gain square 4kT Rs. Is this okay? I just copy this term, 4kT gamma R1 square divided by Rs, divided by the gain square, divided, normalized to 4kT Rs, okay? What do I get? 4kT is gone, and then I have 4 here. So this is 1 plus 4 Rs squared divided by R1. That's the first thing. And then here I have kT is gone. 4 is gone with this guy. Rs is gone because Rs divided by R squared times Rs. Then plus gamma. Where? Yeah. Ah, thank you. 4Rs. I say something. This is 4Rs. Very good. Still very large dB, right? If gamma equal to 1. But we're getting there. We just learn different things, right? But at least here you see that I might have a larger R1 than this one. So this is pretty close to 2. Difficult to say. Depends on how we do it. But anyway, still 2 dB. But you learn how to find the noise figure. Okay? Okay. Now, so just now, we just show you the AC circuit. This is wrong. Because you need to bias this one. You need to have a DC current going through this branch. Right? It cannot just go here directly. In reality, this is what you do. Your signal coupled to C1, but C1 is very large. In AC, it's like short circuit. That's why you see what we have drawn. But then you actually need a current source or a resistor to bias it. That is the real circuit for common gate amplifier. And then if I bias it, it means I'm going to get extra noise from the M2 or RB, right? So the question now is, which one give me more noise? Which one give me more noise? So to compare it fairly, right, we need to let both circuits who have the same ID, right? You do make sure they have the same ID. If they have the same ID, they have the same GM, everything is the same. The difference is just that you're biasing differently. Make sense? In that case, then what do you get? Then the noise due to M2. The noise due to M2, of course, is a current noise, right? Because I have a noise here. I'm going to model it as a current noise, which is IN2 square. What is this? 4kT gamma GM, right? It's still 4kT gamma GM. But I want to compare it, so I'm going to change GM to what we learned earlier, 2ID divided by VB2 minus VT. Now this one we actually mentioned very early when we talk about transconductance. Transconductance equals to 2ID divided by VB minus VT. Do you remember this? If you forgot, just go through the math. Maybe I can quickly say. And by the way, because I started late, feel free to leave now. I feel I just need 5 or 10 more minutes, but you should leave now if you are. I'm going to record it, right? I'm going to upload. So do not worry about this. So, but I want to make this clear. Transconductance equals to partial ID, partial VGS. So it is equal to W on L mu C of Vg minus Vt squared. If you remember, no square because you take the derivative, right? You see that this is also equal to 2ID divided by Vg minus Vt. Just substitute. Okay, so this is the noise that we get from the from it. Then how about the noise due to the RB? It is 4kT RB, right, for voltage. Am I right? But it's also equivalent to 4kT over RB if you make it as a current. It's becoming very messy. Why? If you forgot, I still want to spend time to talk about this Tiffany equivalent circuit. You can have a noise source like this, Vn squared equals to 4kTr. The whole thing is equivalent to have the R here, and then you have In squared equal to 4kT divided by R. Remember we talked about this before? Any question about this? Did I say something wrong? Yeah, RB, right? And this one, what is RB? RB is just equal to 1 over RB is just equal to ID divided by VB, VRB, the potential across this resistor, right? Because the voltage across this resistor divided by IB is ID is equal to RB. Okay, and feel free to leave. Now I want to compare these two. But remember that I need to M2 needs to be in saturation. That means VDS2 must be larger or equal to VB2. This needs to be at saturation. So this has to be larger than VB2 minus VT. Okay? Now, since we have the same current, of course, it also means that VDS2 must be equal to VRB, right? Because I say everything else the same, so this potential needs to be equal to this potential, right? So then it means that this one is going to be smaller than this one, or at best, they are the same. So as a result, you compare these two, you find that M2 has at least 2x more noise. Because this is 2x larger than this one. This is 4kT gamma times 2ID. This is 4kT times ID. Gamma is going to be large, about 1, right? And these two are almost the same, or this one is actually might be larger than this one. Okay, so turn out is 2x more. So this is a little bit counterintuitive, right? You thought that you add a resistor, you get worse, but actually a MOSFET actually give you more noise. So this is just a good exercise for this. Okay, so I still have, I want to continue. Feel free to leave, really, right? I just feel that because I'm too slow, I just want to finish this. So next class, we can just talk about the design for the project. So one more thing we want to discuss is now what if we have channel length modulation? Earlier I said R0 equal to infinity, right? What if we have channel length modulation? And we told you earlier the Vx divided by Ix equals to R in, which is equal to R1 plus R0 divided by 1 plus GM R0. Why? Here. Here. Okay, it's R0 plus RD divided by 1 plus GM R0, right? So this is R1 plus R0 divided by 1 plus GM R0. Now, originally, you thought 1 over GM is enough to match the RS. But now, no, because Rin is not really 1 over GM. It is this big equation. And what is this? Then let's do a look. Let's try this, right? So I'm going to decompose this into R1 divided by 1 plus GM R0 plus R0 divided by 1 plus GM R0. So usually, GMR0 is much larger than 1. So this is R1 divided by GMR0 plus 1 over GM, right? As GMR0 is much larger than 1. So this means that it is larger than 1 over GM. It just says that if you have channel length modulation, the effective input impedance is 1 over GM. I mean, it's larger than 1 over GM. Make sense? So because of this, right, to match, it's no longer 1 over GM. We need to set RS equals to R1 plus gamma R0 plus R0 plus GM R0. So you need to solve this equation to get the GM that you want. And then you design your transistor. That's just to let you know you have this consideration. Any questions? Yeah. R0 is what? Say again. Yeah. R0 is the channel length modulation of the M1. Right? Originally it's infinity. Then we just need 1 over GM. But now we need to match this whole term, which is actually larger. So you thought that you're matching for 50 ohm, you actually may get 60 ohm. Okay. So the last thing I want to talk about is the gain of a common gate amplifier because we need to use it. And is that when we have channel length modulation, it's more complicated. We say it is GMRD, right? Just now doing the common gate. But if you have channel length modulation, it is like GM plus 1 over R0 times RD parallel R0. So why do I want to say this? Now I want to study. If I have channel length modulation, what will be the gain of this circuit, right? Last time I say the gain of the circuit is this one. R1 divided to RS. So now if I have channel length modulation, what is that? So I'm going to just do it a little bit faster. Again, I have V out divided by V in equals to V out divided by Vx, Vx divided by V in. I decompose into different parts. What is V out divided by Vx? Now we included the channel length modulation. Earlier we say it's GMRD. Now it is GM plus 1 over R0 times R0 parallel RD. This one. I'm just getting the gain of the common gate amplifier. Okay? And then Vx divided by, this is R in divided by Rs plus R in, right? But because of channel length modulation, I actually have more terms. So it will be GM plus 1 over R0, and then I do R0 RD divided by R0 plus RD for this parallel term. But for input, remember, it is actually changed because now I match it. I actually match it with R1 plus R0 divided 1 plus GM divided R0, right? So I just plug in those I have. I have R1 times R0 plus R0 divided by 1 plus GM R0, the whole thing divided by RS plus R1 plus R0 divided by GM R0. Very troublesome, right? Actually, no need to do that. Because if we match with channel length modulation, this is just equal to half. Because I match it, right? So the gain is still the same, right? So it is going to be 1 plus GM R0 divided by R0, RD divided by R0 plus RD, 1/2. Okay? So with this, then you will get 1 plus GM R0 times RD divided by 2R0 plus RD. But I did not show it. This is just equals to R1 divided by 2RS. If RS equals to R1 plus R0 divided by 1 plus GM R0. If we match it, this 1 plus GM R0 divided by, I should not use RD. This should be all be R1. I'm sorry. Right, but so this one, let me put it as RD here. Right here, RD equals to R1. Right, so this one is just the same as RD divided by RS. So it looks like I do everything, but not useful. The message is just that if you have channel length modulation, you need to match the input impedance to this equation instead just 1 over GM. Once you match it, the gain will still be the same, which is RD divided by 2RS. Because now RS is this complicated term, not just 1 over GM. So it is still the same. That's all I want to say. Okay, thanks for staying. That's it for today.